Hey everyone, welcome back. Today we're going to do something you may not have thought humanly possible. We are going to find the slopes of things, the steepnesses of things that are not lines. First, let's start with a line. As we all know, the way to quantify the slope, the steepness, at any point on a line is just to do rise over run. The steepness is the same no matter where you are on the line. You're always at a place of equal steepness. In this case, it's going to be 2. But again, what if we wanted to find the steepness at a point on a graph that was not a line? What if it was some curvy boy like this guy? What if we wanted to find the slope at just any random point? I mean, the slopes are all different. They're different steepnesses, different slopes. So a different approach is needed. We can't just say rise over run anymore. That won't work because the steepnesses are different depending on where we are. So what is this approach? Well, how about we start with a simple kind of curve, a nice parabola, x squared. And let's have ourselves the point 3, 9. And let's try, what's the goal? Let's set the goal to try to find the slope. Try to find the slope at that point. So there's that point down there. The x-coordinate is 3, the y-coordinate is 9. And I'm drawing my little instantaneous steepness there in pink. And through that instantaneous steepness, right on through it, I'm shooting off a line in gold. And he has a special name. That slope, the line that's passing through it, is what's called a tangent line. All it is just a line that passes through the little instantaneous steepness you have drawn at whatever point you're interested in. So again, that line is called the tangent line. It quote-unquote goes through the little instantaneous steepness at that point. That's your point of interest. Alright, now to that picture, just the picture's been replicated. I'm going to draw another line. It's going to go through 3, 9, but it is not going to go through the instantaneous steepness. This kind of line has a different name. He's not a tangent line. He's something else. So, like the tangent line, he goes through the point 3, 9, but he does not pass through that instantaneous steepness. We call him, therefore, a secant line. Again, not the tangent line. Again, they both have the property of passing through the point of interest, but the steepness of the line in blue is not the steepness in pink. The steepness in pink is the steepness of the line in yellow. So why in the world am I dealing with secant lines? Well, that'll become clear. Let's take that same picture. Just take that same picture. Let's draw another secant line. We're going to add to that this secant line in blue. There he is. Now notice. Well, you'll notice something soon. I'll draw the picture again, but notice what I'm doing. I'm scooting the secant lines, or if you want to think of it as one secant line, you can. I'm scooting the secant line in blue back towards the tangent line. Just scooting him right on back, seeing what happens, seeing what the consequences are going to be. And to get a better handle on those consequences, let's replicate the same picture again. But let's draw another secant line. Look at what's happening. As I scoot my secant line right on back, scoot it on over to the left, the closer and closer the secant line gets to the tangent line, the closer and closer it gets to actually becoming the tangent line. And that's a key point. It's closer to becoming the line in yellow, the tangent line itself. And let's draw another secant line. Notice it's just inching so close. It's so close to being the secant line. This is the tangent line, but it's not quite there. To emphasize the point, I guess I'll draw the line in gold just a little bit straighter, like so. There we are. So that most recent secant line in blue doesn't quite match the tangent line, but it's awfully close. And a key takeaway of that is that the closer the secant line is towards becoming the tangent line, the closer it is towards the tangent line, the closer the slope of the secant line is to becoming the slope of the tangent line. Let's call the slope of the secant line just m sub sec, and the slope of the tangent line eb sub tan. Now, once again, I raise you the question. What was the point? What is the point of these secant lines? What makes them so useful? Why clutter our drawing with when we have these? We got our perfectly good tangent line. Well, the answer is simple. Unlike for a tangent line, we have a formula. We have a formula for the slope of a secant line. Why? Well, because it passes through two known points. And if we know 2 points, you best believe from Algebra 1 and geometry, we can find the slope of that line. We can find the slope of the line like so. Again, just utilizing Algebra 1. The slope of any of those secant lines in blue, m sub sec, is going to be y2 minus y1 over x2 minus x1. Or throwing function notation, y2 is f of x2, y1 is f of x1, all divided by x2 minus x1. Now then, let's put some stuff in our picture. Let's call that second x-coordinate of that blue dot, let's call it 3 plus h. Again, it looks weird, but let's call that second x-coordinate of the blue dot 3 plus h. Let's do it again, and let's do it for a third time down there. By the way, h is the separation distance between 3 and 3 plus h on the x-axis. And notice, we'll talk about this more in a second, but notice h is getting smaller and smaller and smaller as a secant line gets closer to the tangent line. So if the dot is 3f of 3, that's the point of interest, then the blue dot is going to be 3 plus h, comma, f of 3 plus h. So point of interest, 3, 9, is 3f of 3. Point at which the secant line hits the graph is 3 plus h, comma, f of 3 plus h. And that gives us a very nifty way to rewrite the m sub sec formula, the slope of the secant line formula. It comes out to be like so. Slope of the secant line, f of x plus h, or in this case 3 plus h, minus f of 3, all over 3 plus h minus 3. The numerator nothing happens to it, but the denominator is a nice h. And that makes sense because we are running h. We are running h on the x-axis. And now the key computational insight is this. Again, I alluded to it earlier, but as h gets closer and closer to 0, the slope of the secant line approaches the slope of the tangent line. And now all this language of getting closer and closer to and approaching, this is the natural playground of, you guessed it, ladies and gentlemen, limits. So to express this same idea, but more eloquently and more mathematically, the limit as h approaches 0 of the slope of the secant line equals the slope of the tangent line. In this case, the slope of the secant line is f of 3 plus h minus f of 3, all divided by h. So let's analyze him. Let's tease out some of his consequences. So for this problem, limit as h approaches 0 of f of 3 plus h minus f of 3 all over h is going to be the slope of the tangent line. Again, now let's compute that left side. Let's compute it just using our knowledge of limits and algebra. First, we assemble the pieces. F of x is x squared, so f of 3 is 3 squared, which is 9. So f of 3 plus h, we stick all of that in for x, square that whole thing, and we get 9 plus 6h plus h squared. Now we take those two dots above and we form a third dot, f of 3 plus h minus f of 3 all over h, just by throwing our pieces in. And once we got that third piece, algebratized a little bit, simplifies to 6 plus h, we can very nicely, very crisply take the limit of that thing. So the limit as h approaches 0 of the slope of our secant line is the limit as h approaches 0 of 6 plus h, which is 6. So appreciate what we've just found. We have found the slope of the tangent line to the graph at the point 3, 9. In other words, we have just found the instantaneous steepness of our curvy parabola at the point 3, 9. Appreciate just how much of a infinite expansion this is to our mathematical abilities. We are no longer limited to find the slopes of lines, ladies and gentlemen. We can find the slopes of any curvy thing at any point of interest. Which brings us to a nice generalization. So rather than 3 f of 3, rather than parabola, let's just say the curve is some general f of x. Let's say our x coordinate is just some general a with a corresponding generic f of a for a y coordinate. And that means the slope of that tangent line, which I have dotted in yellow, the instantaneous slope in pink, is given by that formula right there on the right. And this slope, by the way, expressed generally, has a very special name. It's the derivative of f of x evaluated at the x coordinate of interest, x equals a in this case. The way we notate this is like so: f prime of a, f apostrophe a. It's read f prime of a, and it equals the limit at h approaches 0 of the slope of your secant line. By the way, the slope of the secant line is sometimes called the difference quotient. So in the remainder of this video, you will hear me saying slope of the secant line and difference quotient interchangeably. Okay, with our tool chest adequately built up, let's tackle a more difficult problem. So here's a graph. Here's our function. Here's the graph on the right. I want us to answer two things. Visually, what is f prime of 1? And then computationally, what is f prime of 1? So visually, f prime of 1 just means the slope, the instantaneous slope of lowercase f, plain old lowercase f, at the point 1 f of 1, which in this case comes out to be 1 comma 4. So that instantaneous slope there in blue, that is the value of f prime of 1. And we compute it just like we did for the parabola, but you'll notice the algebra is going to be more difficult this time. So f of x, use that to assemble your pieces, f of 1 plus h. That 1 plus h is going to be difficult because there's a cube in here. There's a cube, which creates a difficult FOIL, but you FOIL that out, you get that first term in parentheses. Then you got to FOIL the quadratic, and you get those. And I'm underlining my like terms in the same colors, so green for h, red for h squared, and I throw those in my difference quotient. I throw those in my secant line slope. Do a little bit of algebra. Factor out the h's cancel, and I get h squared plus 5h plus 7. Now a final step, limit of the secant line slope is the tangent line slope. It is the instantaneous steepness. In this case comes out to be a nice 7. So the slope right there on the graph is 7. That's amazing when you think about it, just how much of a increase this is to our mathematical arsenal. Okay, I'm going to pause the video and try this one on your own. Find f prime of 5 if our regular function is plain old f equals x squared minus 6x plus 9. So pause the video and try this on your own. Okay, so again, assembling our pieces using f of x. F of 5 is 4, f of 5 plus h. It's a bit easier than the last problem because we don't have that cubic, so the foiling isn't too bad. Simplifying, and by the way, when you're simplifying here, be very careful with your negative signs. But that's the main thing you want to watch out for. Be careful about your negative signs. Throw them in your difference quotient. Throw them in the slope of your secant line. And take the limit of that simplified product, simplified thing, as h approaches 0. And when we do that here, we get 0 plus 4, or just 4. And that's all there is to it. But you may be wondering, what is just a plain old derivative? I've only introduced the phrase derivative, the word derivative, in terms of the phrase derivative evaluated at x equals a, but what about just the plain word derivative? How do we define that? Well, here's the definition. It's more robustly called the limit definition of the derivative. And it goes like so. Provided that the limit exists, the derivative of f or y, we can call either a function either f or y, the derivative is a function generated by the following limit. So notice, it's the difference quotient, it is the slope of the secant line, but instead of an a, I have an x. It's the most general expression. It's just I'm leaving it as an x. And the way we denote that guy is as f prime, or as dy over dx, which stands for the infinitesimally small change in y over the infinitesimally small change in x. That's how it generates instantaneous steepness. But yeah, it has many forms, has many faces, and we want to know all 4 because we're going to use all 4 extensively in math. You'll see all 4 extensively in physics and engineering, so you want to know all 4 of those forms very well. And this allows us to mathematically write all 4 forms of our derivative like so. Again, these all mean the same thing. These all stand for the same function generated by that limit on the right. Now to really hammer in the idea of a derivative, using the limit definition, let's find a derivative. Let's find one. Let's use the same function we used previously. X squared minus 6x plus 9. Again, now we assemble our pieces. F of x, that's given to us. F of x plus h, we simply replace x with x plus h and do a bit of algebra and simplify. So when we simplify f of x plus h, let's see. We get that. We could drop our parentheses and yeah. Again, guys, be very careful when you're dealing with these parentheses. For example, especially when you plug things into your difference quotient. But now look, things are going to cancel. X squareds cancel, minus 6x cancel, the plus 9s cancel, and that leaves us with an expression that has all h's in the numerator, which allows the h's to cancel. By the way, make a note to yourself, the h's are always going to cancel. If your h in the bottom doesn't cancel, you have done something wrong. Something has gone wrong in the problem, because the h in the denominator should always cancel. But yes, I stick that secant line slope, I stick that difference quotient right next to my zero limit. I take that zero limit, and I get my derivative being 2x minus 6. But what the heck does the derivative do? What does it do? This is the big idea. It is a slope reporter. It reports on the slope at any x coordinate of your point of interest. So one way we could have done every single problem we've done so far in this video, we could have first found the derivative. For example, in the last problem, we could have first found the derivative and then plugged 5 into our derivative to get 4, just like we did with the other method. Likewise, if we want to find the slope of our parabola at x equals 100, the slope is going to be 194. Again, visualize this. That's the slope at the point 100, comma, f of 100. So an amazing result, amazingly powerful. It's unprecedented. You wouldn't think that you would be able to do this, but you can. Well, all right, with all of the pieces on the table, let's end with a bit of a doozy. Let's find the derivative of something kind of ugly, like a square root. Not a nice polynomial, but a square root. And then we're going to use that derivative to find not the slope. It's not the instantaneous slope at the point 16,4, but the equation of the tangent line at the point 16,4. So first we fall back on calculus, find f prime, find our derivative, and notice when you get to this step here, with square roots you want to multiply that by that conjugate there in yellow. Top and bottom conjugate in yellow. This will allow the h in the denominator to cancel. Again, that h always cancels, and here it cancels like so after you do conjugation. After they cancel, you are in prime position to plug in your limit value, or the h value in this case. H is approaching 0, and you get your derivative being 1 over 2 root x. This function is the slope reporter for f of x equals the square root of x. But I don't want just slope for this problem. I want an equation of a line. I want the equation of the tangent line. And either form is fine, either y equals mx plus b or the point slope form, but I'm going to go with the former, the y equals mx plus b, the slope intercept form. First thing I do, I want to find that m value. I want to find m sub tan. Well, to do that, I use calculus. I use my derivative. My slope reporter is 1 over the 2 root x. I plug 16 in for root x, and or 16 in for x, and I get 1 over 8. This is telling me that the instantaneous slope of the graph, so the square root of x, at the point 16,4 is 1/8. The instantaneous slope there in pink is 1/8. But now what is the equation of that dotted line I've drawn? That's what I want to find. I want to find the equation of that dotted line. So the slope is not enough. I need a b value. But friends, this is where calculus is over. To find b, we just need to plug in our slope, plug in our point, just utilizing algebra, geometry, foundations, pre-calculus techniques, and we solve for b. In this case, b comes out to be positive. Just a nice positive 2. And with that, we have solved for our equation. Y is equal to 1/8 x plus 2. Again, our slope's down, derivative's down below, and our equation of our line is up top, both boxed in white. So big picture stuff, guys. The derivative lets us find the slope of infinitely many shapes, infinitely many curves. It's quite powerful stuff. And sometimes for problems, finding the derivative takes a different procedure. Like in this case, conjugation. Some problems will want you to find the equations of tangent lines rather than simply slopes, but you proceed the same way. Notice for this problem, the only extra step was a pre-calculus step, just finding the b value. So more pieces for some problems, but all in all, it's not too bad. Just for some practice, it's quite natural and quite edifying. Again, this is the first extremely important result in Cal 1, and we will see some more in Cal 1. You'll see more in Cal 2 involving area and length of weird shapes, and it all utilizes the language of limits. Later.